the nucleus. The first one is nuclear fission. Nuclear fission means to split the atoms, to split the nucleus. And the way to do that is to bombard an atom, a very large atom, for example, uranium, with a neutron. So uranium or plutonium are the nuclear fuels that's used in the nuclear industry. Very large atoms that can be split. So if you bombard a nucleus of uranium with a neutron, what you'll see happen is the uranium will split in two. And when this happens, when it splits in two, you get a lot of energy off. And this energy is created and given off. Very, very large amount of energy. But what also happens is you get another 3 neutrons coming off. So you've put 1 neutron in to split it. You've got the 2 new nuclei, which will be not uranium anymore. In this case, it's barium and krypton, 2 new nuclei. But you get 3 more neutrons coming off. And remember, this gives a lot of energy. Neutrons, you get something called a chain reaction. A chain reaction, let me describe it here. So here's a neutron coming in. Neutron splits the atom in two, giving off a lot of energy, and also giving off 3 new neutrons. Now, if those 3 neutrons go off to collide with 3 new uranium or plutonium nuclei, then you will get 3 more reactions, 3 more splitting of the nucleus, and there are 3 more reactions giving off 3 times the energy. And if you follow the logic through there, we'll get another 3, 3, and 3, so another 9 neutrons, which can cause that. This is called a chain reaction, and this is how nuclear disasters can happen if it gets out of control.
Nuclear reactor. A nuclear reactor is a device or a furnace where controlled fission chain reaction is carried out and the energy released is used to generate electricity. Here you have an external view of a pressurized water reactor or PWR. Click on the containment chamber to view the parts of the nuclear reactor core. The reactor core, where the nuclear reactions take place, there are the fuel rods, the control rods, the moderator, and the coolant. Outside the core there is a turbine, a heat exchanger, and a part of the cooling system. Click on the labels to know their function. Fuel rods. This is how the fuel rods are arranged in a reactor core. Inside each fuel rod, there are hundreds of pellets of enriched uranium fuel stacked end to end. A neutron is used to trigger the reaction. A suitable neutron source is placed in the neighborhood of the fuel rods. The neutron source is not shown here. Control rods. Inside the core there are control rods to capture neutrons. An example of such a material is cadmium. These control rods are connected to machines that can raise or lower them into the core. Coolant. A coolant is used to absorb heat from the reactor core. Most of the nuclear power plants use water as coolant. In many of the reactors, the coolant and the moderator are one and the same. Moderator. The moderator is used to slow down the high-speed neutrons. If a neutron is moving too fast, it will pass right through the U-235 nucleus. It must be slowed down to be captured by the nucleus and to induce fission reaction. The most commonly used moderator is water. Protective shielding. The reactor core is given a thick protective concrete shield so that there is no leakage of radiation. Generation of electricity. When the neutrons strike U-235 rods, it splits into barium, krypton and neutrons. The position of the control rods are adjusted in such a way that only one neutron is left behind to continue the chain reaction. At this stage, the reactor attains criticality. The coolant is heated by the energy released during nuclear fission reactions taking place inside the core. However, this hot water does not boil because it is kept at an extremely intense pressure. This high pressure raises its boiling point above the normal 100 degrees Celsius. The hot water, being lighter, rises up and enters the heat exchanger through a series of pipes. The water, which is the moderator and the coolant, is radioactive and hence it cannot leave the containment chamber. Its heat is transferred to non-radioactive water in the heat exchanger. The metallic pipes conduct heat from the moderator to the normal water and convert normal water into steam. This steam moves the turbine. The turbine in turn moves the coil of the generator to produce electricity. What happens to the coolant and water? The coolant, which is now at a lower temperature, is then pumped back into the reactor core. The steam, which is also at a lower pressure, is cooled in a condenser and circulated back to the heat exchanger. Many nuclear power plants use steam towers to cool this water with air. These are generally the buildings that people associate with nuclear power plants. In the reactors that do not have towers, this water is purified and pumped into the nearest body of water, and cool water is pumped in to replace it. Other types of reactors are the heavy water reactor, HWR, and boiling water reactor, BWR. A heavy water reactor uses heavy water as a moderator instead of normal water. Heavy water can also be used as a coolant.
The other type of nuclear energy can be from fusion. So fission was about splitting the atom. Fusion is about joining or fusing nuclei together. This is what happens in the sun, in our sun and other stars. So this is what happens. Two protons can join together, quite complicated, but can join together with neutrons until you get a helium nucleus. And again, you get off a lot of energy, and you've got this alpha particle here, which is a helium nucleus, and two more protons which will go ahead to join together and form more helium. So stars is a nuclear fusion reactor, if you like, where protons, which are hydrogen, is turned into helium. When hydrogen is turned into helium in this process, nuclear fusion, you get a lot of energy. So our sun has been a nuclear fusion reactor for thousands and thousands of years, giving us all this energy. Eventually, all of the hydrogen will turn into helium. It will therefore run out of fuel and eventually die. But that's many, many thousands of years to